Okay, you can introduce the session, Martin.
Thanks, Mike. Sorry about that. Jumping the gun there. So delighted to welcome everyone to this first block of parallel sessions. A very warm welcome to our session on LISA data analysis. My name is Martin Hendry from Glasgow University, and it's my pleasure to welcome our speakers for this session and indeed our audience for this session. Our numbers have been growing steadily for the last few minutes. So you're very welcome. The format, unlike our plenaries, which are in LISA webinar format and Zoom webinar format, this time we're back in just regular Zoom meeting. So that means that when we come to Q&A, people can feel free to unmute themselves and indeed switch their cameras on if they wish and ask their questions. But I would invite you to use the chat to ask questions if you prefer. That's a good way, for example, to ask questions as we go along, but we won't interrupt the talks. We'll keep the questions until the end of each talk, just to make things more manageable. We also are live streaming on YouTube. There may be some questions will come in from there as well. So I will do my best to field all of those. Just a quick word to our speakers. Let me note that we have 20 minutes allocated for each talk. So that's nominally 15 minutes of talk plus 5 minutes of Q&A time. So I will let you know when you've got 2 minutes left. And frankly, there's probably no easier way to do that than for me just to say that out loud. It saves you having to worry about keeping an eye on the chat. So I will do that. I will try not to be too rude and interrupt you midstream. But we are in fairly good shape time-wise for this session, because in fact there are only 5 talks in this session. So we've got 3 before the break and then 2 after the break. So it's LISA data analysis. We have multiple data analysis sessions. This is the first of 3. And before the talk, we have, before the break, we have talks from Stas, from Michael Katz, and from Sayantani Data. So it's my pleasure to introduce our first talk, which is Stas from the APC CNRS in Paris, who's going to talk about global fit, find, remove, iterate, and enjoy. And I'm sure we will all do the enjoy part, as Stas tells us about the first 3. So thank you very much, Stas. Over to you.
Thank you, Martin. Let me start to share my screen. Share and slideshow. One more second. Laser pointer. Can you hear me and can you see me well?
Yeah. Loud and clear.
Very good. So let me start. And this work was done in collaboration with quite a few people. And Silvia is actually giving a talk. That's the person here, and other parallel session right together with me. I will introduce global fit in LISA data analysis. I know that Tyson did a great job yesterday. I really enjoyed listening to him. But nonetheless, let me just give you a few bullet points. So why we need a global fit and what is global fit? The thing is, LISA will be signal dominated, and we will have many gravitational wave signals, thousands of gravitational wave signals, and many of the signals are long-lived. So some of them will be living present in the data throughout the whole mission. Some of them, like massive black holes, will last from, let's say, a few hours to a few months. But all in all, we have a lot of signals. They overlap in time, they overlap in frequency. Some of them talk to each other so they can see each other's presence. Some others don't. And therefore, just going after one signal at a time and ignoring others, it would be wrong things to do. And we know about this. And that's what this global fit is about. In addition to all of this, that we have very rich astrophysical content, we will have, in resolvable signals, we also will have signals which are from unresolved, in the meaning that, those are signals which are, let's say, subthreshold events, subthreshold gravitational wave signals, which we're not confident about its detection and whether they're present or not, and therefore they will contribute to the total noise budget, and sometimes they actually exceed the instrumental noise. And in addition to this, we do expect some non-stationary features in the data, like gaps and glitches, and the noise level itself is breathing, will be function of time. And of course, we might have big surprises in LISA, like we did for first gravitational wave detection with the LIGO detector. And this surprise could be in the wave rate and in the parameter distributions. So let's move on. I will go quite quickly across this because Tyson already introduced this. This is the data called Sangria, where we actually probing our global feed. It contains instrumental noise in red. It contains verification binaries in yellow. This time the main data. It contains 30 million of galactic binaries. Of course, most of them are not detectable, but they will create the stochastic signal, which I mentioned before. And we have this in purple massive black hole mergers. If you zoom in, so sometimes you can see this is signal plus noise, but the signal is so loud that you don't even see the noise. Some others are much quieter, and you see they're actually below the noise. And if you look in time frequency, you can see clearly the tracks chirping and merging tracks of massive black holes, and you can see horizontal lines corresponding to the most bright galactic binaries. So this is our playground. So those are signals, these are emerging black holes. And let me first introduce you a global overview before I go into details. So what we are trying to do, again, Tyson did great job introducing, one variant of this global fit. I'll give you a slightly different variant of this. We start with the data. We pre-process the data so that, and we analyze it visually like we just did it right now. We see already massive black holes. We see some galactic binaries. And what we see the most is this bright mergers of massive black holes, what we call elephants. So what we want to first to do in this step is we want to remove these elephants from the data and then go after something a bit weaker. And so what we'll produce is reduced data. I call reduced data is data, or sometimes it's called also residuals, is a data minus some gravitational wave signals. And then we will make two parallel steps. We're searching for galactic binaries, and we will be searching for massive black holes. And we consolidate the results, and we check whether we are done or not, and we iterate this step again and again until we're done and save the data. So, and I'll now go a bit more into details of each step. I'll start with this step. It's what I call divide and conquer, or removing elephants. So as I said, we have these bright massive black holes mergers, and they clearly visible, especially if you whiten the data, or in other words, you apply a filter which removes high and low frequency component of the noise. You can see even the weak signals becomes visible in whitened data. So it's just visual inspection. You can see how many signals there. What you can do, you can, well, you still need to remove them, right? And I want to do it preliminary, not very accurately first, just to the level of the noise. So I will take a chunk of the data around this each merger, which I see by eye, around 2 weeks, and I will have very crude but very preliminary, very approximate gravitational wave models, which neglects laser motion, which neglects Doppler modulation. So I will not have sky location, and I also maximize over many extrinsic parameters. So I will be only having masses and spins, which I will be fitting for. And still, I need to find this masses and spins of these massive black holes, merging massive black holes, and I use a grid-based method with mesh refinement based on the Vegas algorithm. It's something similar to when you're trying to produce histogram, and you start with the equal bin size, but then you resize the bin according to the number of events, or in this case, and according to the likelihood in each evaluated at each this hyperbox, and then you resize it according to preserve the probability in each hyperbox. So it's something similar to when you're trying to plot this histogram by doing different bin size. And that's what happens. You start with the equally distributed grid, and after a few iterations, very fast, after a few minutes, you will have this refined grid where you see the more dense point where there is a higher likelihood and less dense point when there is no signal. So that's one of the methods, and for more details, you can look at the pre-recorded talk by Sen-Wen Deng. Alternatively, you can start with just stochastic method and run your favorite stochastic method like Markov chain Monte Carlo or genetic algorithm, and you're trying, here's an example from Sylvain, when you're trying to run a stochastic Markov chain Monte Carlo. Again, very crude, but you already see the signal and you preliminarily see where the parameters are. Now you want to restore the extrinsic parameters. What you can do, you can start with the already preliminary guess from the previous step, when you know intrinsic parameters, so masses and spins, and you run another Markov chain on the extrinsic parameters, and that's what you will get very fast. Again, these steps usually takes between few minutes to few 10 minutes. So, and that's allows you to remove elephants to a very high level. So you can see slightly residuals here, but I don't care because I will be refining the search results in a minute. I managed to remove elephants down to the size of the cat or dogs, and now I'm good to make next step. In the next step, I will be searching independently for galactic binaries and massive black holes refinement. And then I will consolidate result and iterate. So for galactic binaries, similar to what Tyson has presented, we split data in frequency bands, roughly around 1 microhertz. It's a very narrow band. However, we're keeping the boundaries flexible. So let's look at this black segment here. There is also a red segment there and neighboring purple segment there. And our boundary is actually semi-flexible because we will be looking at the left and the right of the black segment. So what we're starting to do is, again, similar to what we did with massive black holes. We use f-statistics, so we're maximizing over some parameters of the binaries, and we're looking on a kind of grid for candidate events. So each candidate event will be followed by parallel tempering Markov chain Monte Carlo to refine its parameters, to find its better. And then first signal will be added to local catalog. And then we're going after second source. And every time when you're adding a source to the local catalog, we're checking if it has overlap with signals on the left and signals on the right, because we're running in parallel searches on each of these subsegments. If the signals are overlapping strongly with its neighbors, the neighbors are added to this pipeline to make sure we're not cutting signals in parts and having problems with fitting. Now, basically, it's again, we're adding signal by signal. However, it's not very good. So at some point, very quickly, when we're adding already two sources, we're actually running parallel tempering Markov chain with the two sources, making sure that if they talk to each other, they refine its parameters. When we're adding third source signal, we're again running on three signals, trying to make sure that all the correlations between signals taken into account. Moreover, we need to terminate this loop somewhere, and at each point when we're adding the extra signal, we're running model selection. So let's say our previous model had n signals, and we have another candidate coming up. So we're making model selection between n signals and n+1 signals based on the base factor. And if data supports n+1 signals is added. If not, we're terminating this loop at n signals and saying that's what we have found. And for details, I invite you to see pre-recorded talk by Eric Plagnuol. And so very briefly, results in a few frequency bands. So this is 4 millihertz. You see the color, the signals which we have found in the data, and this in the blue dashed and solid lines are residuals. Solid lines is what we found as residuals, and dashed is a theoretical limit, assuming that you could perfectly remove all the sources with SNR larger than 8. The interesting part, you can see there is only noises seen here and here. Everything else is basically covered by signals. When you're going to 5 millihertz, situation is slightly better. We start to have a bit less sources, but nonetheless, again, if you see the noises, noises are only partially seen in this frequency band, most of it covered by signals. When you're going to 6 millihertz, situation much closer. So basically, if you see dashed and solid lines very almost on top of each other, and we're recovering quite well signals. So between 3 and 6, that's what the most confused region of the parameter space, where the most signals are present. So next step is going right. Now we want to also to search for massive black holes. We already have preliminary parameters of these massive black holes, and we start from there. So we're not neglecting this. However, refining massive black holes is still non-trivial thing, even if you have preliminary guess. And we're making two tricks to make it happen, to find massive black holes very well. The first trick is if you look at the parameter space, so basically this is corner plot for parameters for massive black holes, you see a lot of correlations present there, and the structure of the posterior is very rich and quite non-trivial. However, you can do the mapping between physical parameters to some other parameters which easier to sample. So you see most of the correlations are gone, and they're more Gaussian looking posteriors. That's the first trick which we're doing. And second trick is thanks to Cornish and his postdoc in paper published in 2020. It's when they're suggesting so-called heterodyning likelihood in order to to speed up the calculations. What you do is like in heterodynamic when you're removing carrier frequencies, so the fastly oscillating part. Here we're not removing a single frequency, but we're removing the best guess of the signal. So basically we're removing evolving frequency in time. And at the end, what is left is residuals which are slow changing function in frequency and in time. So that we basically, again, similar to radio technique where you're removing the carrier signal, here we also end up with a slowly low frequency component, which is much easier, requires much coarser grid in time and in frequency to sample, and therefore requires to speed up likelihood calculations tremendously. So these are the two tricks which we're using for massive black holes. Now, in a few more last slides, I want to introduce a few things which actually I did not mention. It's kind of swept under the carpet, and now it's time to bring the carpet up and see what is underneath. So the first question is the noise level. The noise level is unknown. Even instrumental noise in this data is unknown. To some, it has some priors, but nonetheless, it's not exactly known. And moreover, the part of the noise is created by galaxy itself. So we need to evaluate the noise level. What do we do?
2 minutes left, Stas.
Thank you, great. We are starting with a guess for the noise level based on power spectral density estimation. And then at the end, when we found the signals, we plug a noise model with the found signals and reiterate it together. Some sources will be lost. Some of them will be slightly enhanced. Depends on our initial guess of the PSD. Then time iterations. The data comes every day, and we need to perform the analysis in time iterative way. And it looks like actually it helps, especially if you just analyze galactic binaries, adding data every 3 months. It's easier to look at the source when you have 3 months of data, and if you're adding more, you're just refining your already found parameters. And of course, the question, where do you stop the iterative procedure? And of course, since we know the answer, we can look at what is good enough based on the false alarm and comparison with catalog. When you don't have catalog, probably what we want to try to do is comparing parameter distribution between successive iteration steps and see when they stop evolving, they become stable, or similarly, you can do residual comparisons. Of course, you need to penalize for introducing extra sources, extra parameters. However, this penalty should be not strong, because otherwise you start losing the relatively strong signals. And that's actually we already observe in our analysis. And my summary, so basically what we have demonstrated here is all necessary tools and steps to perform the global fit analysis. We have not finished it. Basically, what we need to do in the next steps is to make these iterations and complete the search. And what we need to test is also what the best noise model, which would be easily fit into the residuals, and what would be stopping criteria of this iterative procedure. And I thank you for your attention. I will be happy to answer questions if you have any.
Thanks, Stas. That was great. So are there any questions? Well, let me ask one to begin with. So you began by talking about the removal of the elephants. So can you comment on, how robust that part is? Presumably the rest of the analysis is not too badly affected if one elephant is left behind that is not removed?
Right. So in principle, nothing is really affected besides power spectral density. So we need to do some preliminary power spectral density estimation to start with. We did it for elephants, and then actually there was a little iteration there, but not much. Elephants affect and strongly bias the power spectral density estimation, and that was that's why it was needed. And of course, you don't need to remove all of them. It just helps a bit, but not critical. But the brightest massive black holes, that's what is needed to be removed. But actually, it happens that we could remove all 16 or 15 sources.
Okay, thank you. Michael has a question.
Yeah, hey Stas, nice talk. I was just wondering, you said really quickly about the parameterization of your noise model.
Yeah.
I just wanted to know, just to clarify, if I understood correctly, that you're fitting parameters in the kind of parameterized noise model that we usually use, and not doing it kind of in your like sub bands or something and fitting a point, right? Is that correct?
So we tried to use in sub-bands, but it turned out, so if you look at this data, that there are two solutions here. either noise only or noise plus signals. So you need to connect several bands, let's say like a 4 millihertz with 6 millihertz where noise is more visible. Otherwise, if you're trying to do piecewise in the small sub-bands, you will have, a lot of jitter up and down, especially in the part which is transition between fully confused to non-confused one. And so what we are trying to do now is really broadband noise models, which is has model for the galactic foreground plus instrumental noise at the higher low frequency parts.
Got it. Okay. Thank you.
Thanks, Michael. So are there any other questions? Well, let me ask another one very quickly. You mentioned towards the end the importance of not having too strong a penalty function because it could wind up removing sources. I'm not sure if I quite saw why that should be. Could you say a little bit more about that?
Yeah, so our approach penalty comes with the prior function, okay? Because therefore, it's if you're using very broad priors, you're allowing in a way a lot of false alarm to sneak in.
Yeah.
And as a result, what happens is that what we notice is with our loose and broad prior, the limiting signal to noise ratio for galactic binaries was something 12, and which is relatively high. So when we're trying to do more astrophysical priors, we see that we can do better.
Yeah, thanks. Yeah, that makes sense. Okay, questions coming thick and fast. Let's see if we can squeeze two more in. Jean-Baptiste?
Yes, I was wondering, did you analyze the entire 4 years of data? And second question, how long did it take in total? What kind of architectures did you use? How many CPUs and so on?
Ooh. So it's a 1 year of data which we have. This is simulated data, and we analyzed not full, but we analyzed like 200 frequency bands of galactic binaries data. So we did not analyze whole frequency range. And then the question is how many size samples you want to accumulate.
Yeah.
So to find the signals, actually it is a relatively fast per frequency subband. So it takes half day to few days per frequency band, depends on the frequency. And it's usually run on multi-core, single machine multi-core, similar to what Tyson has.
And so do you run each of the bands in parallel?
Yes, I don't know exactly how Mott made talking to each other, because as I said, neighboring bands, they look at each other.
For the noise, yeah.
Yeah, not for the noise. It's for the even neighboring, if you're cutting signals in halves.
Okay. Thanks, Stas.
Great, I'm muted. Nikos, let's just hear your question before we move on.
Yeah, thank you, Stas. This was very nice. Just a quick one for my curiosity. So I think that you said that you are looking at overlapping segments, right? And then you're checking if there is sources that are in both segments. How do you do the classification? If how do you figure out if it's a source that belongs in both segments?
Yes, correlation.
Correlation. Yeah.
Overlap.
Okay, thanks.
Okay, thank you. Very nice one-word answer. So let's thank Stas again. If you can use the Zoom reactions, I will try to do that myself. And let's move on to our second talk, which is by Michael Katz. So Michael, if you want to share screen. Okay, and Michael is from the Albert Einstein Institute in Potsdam and is going to talk to us about a new GPU-accelerated, adaptively distributed global fit algorithm. So take it away, Michael.
Thank you. So as Martin said, my name is Michael Katz. I'm currently a postdoc at the Albert Einstein Institute. And today I'm going to be telling you about our new GPU-accelerated, adaptively distributed global fit algorithm, which I have been working on with Nikos Karnisis, Natalia Korskova, Jonathan Gare, and Nikolaos Sturgulaos. So I'm mainly going to highlight today, lucky for me, I've now gone after Tyson talked and after Stas talked, which has given me quite an introduction to the global fit. So instead of going through those kinds of things, I'm going to focus on what makes our algorithm different. So as you can see there in the first point, the main thing that we're going for here is to take important lessons from what Tyson and Neil have done, and then produce a new algorithm with it, one that can allow us to investigate different avenues of how to address this very computationally difficult topic. So these next bullet points here I'll address them in succession here as we go through the talk. These are all things that kind of make our algorithm a bit different, except for the last bullet point. I just want to make clear Tyson's codes are publicly available, and our codes are as well, as I'll talk about in my concluding slide. So the main underlying and underpinning aspect of our algorithm is we are trying to do this with GPUs. Now, the reason for this is, as Tyson said, and as you kind of heard a little bit there at the end from Stas, this is a very computationally difficult problem. And that's not a slight against anyone, obviously. This is just the fact of what we're working with. So what we are trying to do is we're trying to approach this from a different angle. And instead of trying to span it across many CPUs and CPU nodes, we're trying to understand the place of GPUs in this grand global fit scheme. So as you can see here, this is kind of our basic setup, but the reason we do this is we get hundreds or thousands of times faster from using GPUs. We do this by evaluating things in large batches, and we basically loading as many of them as we possibly can. And in order to make everything extremely fast, or as fast as we can possibly get it, and as least memory intensive as we can get it, we end up using all residual-based single source likelihoods. So what that means here is, I think Stas kind of briefly mentioned it. It's where we take the current point of our sampler, we generate a template of all of the binaries that are currently there, and we subtract them out. And that's effectively gives us our residual, and then we do likelihoods against that residual. So the base likelihood, the regular likelihood we're used to, is up here in the top. So you would compute this after you have created this amassing of templates in the letter H here. If you add a source like we do in reversible jump, you can add it right here, like you see the letter A right here. And if you do the math, you can get to the point where you see that the change in the likelihood from the base likelihood is given by two single source likelihood terms. And what I mean here by single source is that you ultimately have to calculate the inner product across the width of a galactic binary spectra, which is not wide and is small, something like 256 points or so. So this ensures the fact that your integral or your discretized summation is very small and therefore very fast. When we are proposing a new point for a point that already exists, so we're not adding a source, but we're taking an existing source and updating it, that's effectively the same as removing the old source from the data and adding in the new source. So that's how you can see here, we have H plus A minus R here to represent kind of this changeover of the waveforms. And after you do everything out here till the end, you'll find once again that all of these inner products are single source with inner products that are all extremely, extremely fast. And is this kind of underpinning that we use to kind of design the rest of our sampling. So with that said, the GPUs give rise to what we are calling adaptive distributed Gibbs sampling. So similar to what Tyson and Stas have done in the band structure, I've kind of tried to schematically show that here. As you've heard, there are a variety of ways to set this up. There are a variety of ways to kind of pick your bands. But if I'm not mistaken, in Tyson's setup, and I think in Stas, you can please comment after if I'm wrong, once you have picked the bands, they're generally fixed and generally fix your computational resource distribution. And that is the kind of aspect that we're trying to look at, is how do we adjust this to be to pertain more towards GPUs and ways of kind of loading the GPUs with as much information as we possibly can. So the way that we do that is on the fly, we want to assess which sources are independent of one another in terms of their frequency. And so we can see kind of an example here of that, where if we have our blue and our orange source, we cannot run these at the same time because they affect each other, they're affecting the likelihood, depends on each other. So we cannot run the blue and the orange signals together. But as long as we do some very particular bookkeeping, we can run the green source and the blue source at the same time, because their effect on the likelihood is effectively independent. So with that said, what we do is we set up an algorithm to locate all of the binaries existing currently in our sampler that do not overlap with one another. So for example, in our first group, that looks like this, where we start with our first column. And just to be clear here, the vertical axis is walkers. So the rows are independent of one another already. But our goal here is to kind of maximize how much we can run across all of the walkers and within each walker all at the same time. So if we start here with this blue dot here, we check these first three. We notice that they are overlapping with this blue one, so we don't run those. We find this one is not overlapping with the first blue one, so we run it. Same thing with this one. We check this one. It doesn't overlap with this point, so we run it, and so on and so forth. So the idea here is to kind of iteratively build which sources are completely independent of one another and loading those all onto the GPU at a given time. So as we build this up, this is kind of what it looks like. We start to fill in until we have reached a full coverage over all of our existing sources. And what we do then is kind of, you can imagine it running like this, where now instead of farming out a variety of nodes for the different subbands, what we're trying to do here is kind of conglomerate everything and then split it up across GPUs so that we can keep everything as confined as possible. And part of our goal here, as I'll briefly mention in the end, is we want to try and get around this band structure, or at least minimize it. I think as I showed back here, we want to try no subbands or very wide subbands. So this talk from Stas and Tyson about this, we are trying to do this a little bit differently to investigate how running with or without subbands is useful effectively, and where we can leverage that to our advantage with the GPUs. And as you can see here, doing this type of setup gets us to running about 80,000 likelihoods per second on one A100 GPU. We could probably even make that a little faster with some of the setting choices that we've chosen. This is a bit conservative. But as you can see just from that number, that this is really, the GPU is a really nice workhorse in giving us kind of an alternate avenue for addressing the computational difficulty of this problem. Another really nice new tool that we use is called multiple try MCMC, and I will explain that in a second, but I will start by explaining just regular MCMC. So just as a reminder, you start with a set of parameters here in orange, you propose the blue set of parameters, you accept or reject it, you get the orange if it's rejected. You propose the pink set of parameters, you accept or reject it. In this case, you get the pink parameters, but ultimately this kind of central line of blocks is your chain. These are accepted or rejected based on this acceptance probability shown here. Just in a simplified sense, you can think about it like the ratio of the likelihoods. So if the likelihood of the new point is better than the likelihood of the old point, it will always be accepted. If the likelihood of the new point is worse than the old point, then it will be accepted a fraction of the time. This fraction is governed by this ratio. Now, if we take a regular MCMC proposal that, for example, works 1 out of every 10 times, so you have an acceptance rate of 10%, which may sound low or something, but that's just for the sake of instructional purposes, but also, as Tyson talked about, it is quite difficult to design efficient reversible jump proposals because of the parameter space that we're dealing with. So just for this example, take that to be the truth that this proposal we're looking at succeeds 1 out of every 10 times. Roughly schematically looking, this is what your sampler would go through, where it starts with the orange blocks, and eventually you get 1 accepted where the blue moves over. Now, the thing that we're using, which is multiple try MCMC, is a bit more complicated than that, as you can see, but it's different and it's useful. So instead of proposing 1 blue point, we actually propose 10 of them at the same time. We then pick 1 of them as our actual proposal point by drawing based on its importance weight. And in this case, you can just think about it as the likelihood. So in other words, if we propose to say, for example, add a new binary, and we propose to add 10 of them at the same time, and only one of them finds one, that likelihood will be high, and that will be the one that will be selected out of this 10. Now, the catch here is that you can now no longer compare your new point that you have selected based on its importance weight against the old point, because you will not be satisfying detailed balance. Instead, you have to add 9 auxiliary proposals to add to the one original, so that you now have 10 proposals on this left side and 10 proposals on the right side. And your acceptance fraction becomes dependent now on the sum of the likelihoods of these groups, instead of on the singular likelihoods of the new and old point. And now you can see that down here, and that is literally the sum over the sum of each of them. Now, if you look at this, you may wonder why this is more efficient. You're actually computing 2 likelihoods for every one. So in this case, we want to do 10 proposals, but we actually have to calculate, it's really 19, but okay, we'll call it 20. We need to calculate 20 likelihoods here effectively. But the thing is, with the GPU, because we want to shove everything onto it at once, it becomes much faster to do 20 likelihoods at once, for example, rather than 10 iteratively, sequentially, one after the other. So that's why this type of algorithm can be very useful when using the GPU and for reversible jump. And this kind of brings it all together in the kind of schematic returning to comparison with regular MCMC. This is obviously kind of simplified and not entirely true, but just trying to paint a picture here that if you propose 10 points for every proposal now, for a proposal that is accepted 10% of the time, you will actually propose an accepted point, on the average or whatever, each time. And what this does is it allows for much better mixing of the MCMC chains, I think better convergence in your sampler. And ultimately, I think it's just very good because we can, with GPU, really up the amount of proposals we're using, so we can extend this number of blocks per proposal, basically, and really draw in good proposals for reversible jump MCMC in an efficient way.
That's just about 2 minutes left, Michael.
Sounds good. Yeah, the last thing I will talk about is this SNR annealing search. So as Tyson has talked about, and also Stas, you got to be very careful about how you do the search. Instead of building up over time, kind of like Tyson has done, what we are doing is an SNR annealing setup. So don't worry about any of the numbers on this plot. This is just a schematic to be illustrative once again. So what we do, if you can imagine this gray block, the top of it is an SNR limit. And what we fix is so that the sampler does not allow any sources to exist inside of it that have an SNR below our SNR limit. So as I play this, you'll start to see the SNR limit go down. So this will be iteratively happening in our sampler. I'll pause really quick and just say, you'll see these popping up. They're not filled in yet because we rarely find these sources at their peak SNR, so at their peaks. We usually find them a little bit lower, and that usually comes in through the use of parallel tempering. So what you'll see now is they'll pop in here and show you that they're now detectable. But the key is, once again, we don't allow anything to exist that is below this upper limit. And now you'll see kind of the low SNR binaries pop in. So that's, really in a simplified way, that's what we're doing. We're just preventing low SNR binaries from adding in and messing up our search effectively in similar ways that Tyson and Stas talked about. So this is my concluding slide. So I'll just say a few things in conclusion. And the top bullet point there, you see kind of the main things that we have added to our global fit algorithm that makes it a bit different than Tyson and Stas's algorithm. What we are working on now is scaling up to maximize our source count per band. This is our kind of last successful trial we have on the right side, where we have about 50 sources. We're now running bands with 2,000 sources in them. And so far seeing decent results, but we're not quite there to, they're extremely preliminary. So that's why I haven't shown any of them yet. But ultimately that's what we're working on now, is trying to understand how this large band structure can benefit us. We're then going to do non-stationary noise effects for the LDC2A that Stas was talking about. And I'm going to implement a pipeline that I designed for a previous paper for the massive black hole part of the LDC2A, as Stas also alluded to. And I'll just end by saying, all of the codes I don't know if anyone else heard that, but it just told me recording stopped. I hope that's okay. All of the waveforms and codes that we use are publicly available. The galactic binary waveforms are fully publicly available and available here. If you were at the LBC workshop yesterday, you saw and got a taste of this. The sampler, which we have, is a non-gravitational wave specific sampler, and a set of tools called LISA analysis tools are also publicly available, but they're in a beta version. So if you are interested in using them, please talk to me before you use the beta version ones. But eventually, as we kind of finish up, clean those up, add tutorials, add documentation, these will all be publicly available and for use by the community. And I would just like to end by saying we'd like these tools to be community developed. So if anyone's interested in doing that, please let me know. We welcome it. And I'm happy to take your questions. Thank you.
Thanks, Michael. Very interesting. Yeah, I'm not sure what happened when you heard the recording stopped. It seems to have restarted. It may have dropped out for a few seconds, but I hope it was still streaming to YouTube so we can patch that in. So are there any questions? Well, again, Content has one, so let's go with that.
Hi, thanks. Thanks, Michael, for this very interesting talk. I was wondering, did I understood well that you're grouping the calculations of non-overlapping sources because you're grouping the dot products and not the waveform computations themselves? Or
so just to be a little clear there, because grouping, I think, has a couple meanings there with the GPU.
Yes.
So what we are doing, so our goal is to basically make the largest group of sources that we can run at a singular time that can all be run independently in the current iteration of the sampler. And then once we have, like on the wrong screen here, sorry, I'll just scroll. Hopefully I have that still up. So what happens is we basically conglomerate all of these groups into the largest groups that we can make, and we kind of iteratively run them across as many GPUs as we can, more or less. So we split them up based on their overlap, whether or not their signals overlap, but then we run all of those that don't overlap as a single entire group. And then we just do very careful bookkeeping. So what we're really doing is we're not calculating the likelihood, we're calculating the change in the likelihood. We do an accept or reject, and then we update the likelihood, the overall likelihood, and update the residual based on all of them that are updated in the same data stream, which I hope makes sense. I hope that answers your question.
Yes, okay. That you're updating the likelihoods, and this I had missed. Okay, thank you very much.
Thanks. Let's go to Christopher now. Christopher, are you there?
Not hear Christopher, although it doesn't say he's muted.
Hey, can you hear me now?
Yeah, we can hear you.
Okay, so great. Thanks for the talk, Mike. I was wondering about the annealing you showed and the fact that sources were only found after you got beyond the SNR peak.
Yeah.
And just wondering, is there a relation between how much you need to drop before you find a peak? Does it vary across parameter space, whatever sources you've got?
So one thing I really haven't included here is for the really loud sources, we actually do a bit of an iterative subtraction to start, just because this SNR annealing part, if you want to be very careful about it, it kind of takes a long time to get from the loud SNR sources to the low SNR sources when there really aren't many of them. So just to be clear, some like the loudest ones, we iteratively subtract up front. Once it gets down to the low SNR sources, that I think is where we have to be really careful. And that's where we have effectively mainly used this algorithm. I would say the one that we're running right now with the 1,000 source bands, we stopped at about an SNR of 50, doing the iterative subtraction, I would say. And then what we do is we just run this very slowly. And what we see ultimately is, once you get to the low SNR sources, obviously there's only so much SNR you can latch onto. So for those, it's not too difficult in terms of tuning this. I think the real thing where the real usage of this comes in is with parallel tempering. Some of the higher temperature chains, what they'll do is they will, lock on sources and then over time move them up. And then once they move up, that's when they shuffle down the temperature ladder. So I think maybe that's a better way to look at it is it's pretty hard to find them in the zero temperature chain or in the temperature 1 chain or the cold chain because you're really already at the peak of the likelihood and you don't have a lot of leeway for putting that one source in. So I think I actually saw Neil say this in a comment yesterday during Tyson's talk, is we do see a lot of these kind of shuffling in at higher temperatures, adjusting slightly, and then once they're at the peak, they swap down to the cold chain effectively. So that's kind of how that's done. And I hope that was clear.
Yeah, thanks, Mike. So I guess we should move on. Sorry if there were other questions that we didn't get to, but let's thank Michael again. Thank you. And we'll move on to our third and final talk before the break. And if I can invite Sayantani to share screen.
Yeah, let me share my screen then.
And then we'll introduce you properly. Excellent. So it's my pleasure to welcome our third speaker, Sayantani Datta from the Chennai Mathematical Institute, who's going to talk to us about enhancing the performance of multi-parameter tests of general relativity with LISA using principal component analysis. So over to you, Sayantani.
Thank you. Hello, everyone. I'm Sayantani Datta, and I'm a graduate student at Chennai Mathematical Institute, working with Professor K.G. Arun. And I'm going to talk about enhancing the performance of multi-parameter tests of GR with LISA using the method of principal component analysis. So to start with, we know that the detections of gravitational waves have allowed us to test GR at really high curvature regimes, and one runs into various problems while formulating a quantum theory of gravity in such regimes, and hence there are different modified theories of gravity. So there here shown is a brief classification of these various modified gravities based on Lovelock's uniqueness theorem, where each modified class arises from violating one of the underlying principles of GR. For example, there could be dynamical fields non-minimally coupled to G mu nu, or auxiliary fields to the stress energy tensor. We could also consider Einstein-Hilbert action in higher dimensions. Then there is weak equivalence principle violations due to non-minimally coupled fields to the stress energy tensor. And then, of course, there could be some form of diffeomorphism invariance violations. So given we had some theoretical model for gravitational waves emitted in these theories, we could have put them to test, but in their absence, what we do is do a parameterized test. So for this, we have a very good understanding of the gravitational wave phase evolution under post-Newtonian approximation of GR. So in this plot, you see the different phases in the evolution of the binaries, starting from in spiral, when the binaries are far apart from each other, and in spiral due to a gravitational radiation reaction. So in this regime, the gravitational waves can be modeled using post-Newtonian approximation, and the schematic form is given in the first equation. And in the second equation, the basic structure of the phasing is given. So both the amplitude and phase can be expanded in powers of V by C, which is what is shown here. The phi k and phi kls are called the post-Newtonian coefficients. And these are all functions of the intrinsic parameters of the binary, for example, the mass, spins, and so on. So these post-Newtonian coefficients are quite rich in structure, and multiple nonlinear interactions and physical effects can enter in multiple post-Newtonian coefficients. For example, tail, for example, the 1.5 PN coefficients has both spin orbit interaction contribution as well as tails of gravitational waves. So it's only natural to expect that multiple post-Newtonian coefficients may get modified if the binaries interacted differently in a modified theory of gravity. This gives us a motivation to test for these coefficients and see if they're consistent with the GR value. So for that, we introduce consider this null parameterization, where fractional deformation parameters are added at each PN order. These are denoted by delta phi A. Of course, in GR, their value is 0 and could have any non-GR value in the modified theory of gravity. So as I said earlier, we would actually like to do a test where multiple post-Newtonian coefficients are measured. So this will be called as a multi-parameter test of GR, where both the GR parameters along with multiple post-Newtonian deformation parameters are measured simultaneously. Now, this is a more general and a rigorous form of parameterized test. However, it's really difficult to do this because of the correlations between the deformation parameters. But we did show in these two papers that one can really do a full multi-parameter test where all the deformation parameters up to 3.5 PN can be measured, but using multi-band candidates. These are the stellar mass black holes on the heavier side and some intermediate mass black holes of the order of 100 that can be seen in both LISA and a ground-based detector, and we can use information from both these places that help lift these degeneracies. However, the rates of such events would be really low. So what is now done is the single parameter test, where only one deformation parameter is measured along with the GR parameters. So this is a restrictive and approach, but a useful null test. However, this demands eight independent runs for a single event. So how do you actually overcome this problem associated with multi-parameter test? So since the main problem is the degeneracy, we could use principal component analysis to transform to a new basis where these correlations are basically gone. So in this new basis, we'll define a new set of parameters and we'll call them as PCA parameters. And we actually demonstrated this method on O102 events detected using advanced LIGO. Using a Bayesian inference, and we found that we could detect we could measure the first two PCA parameters well, and they could pick up the true value very close to the mean. But here what we will see if LISA can help us to measure more of these new PCA parameters, and in turn can help probe higher PN orders better. The relation between this, measuring more of these new parameters and probing higher PN orders will be clear as I go forward into the talk. So as an example, I have shown here posteriors on the deformation parameters from 5-parameter test using a system of 6.6 times 10 raised to 5 solar mass. So deformation parameters from 0 to 2.5 PN are simultaneously measured using Fisher information matrix, and we can directly get the errors from the covariance matrix. As you can see that the contours are all tilted, and it tells that the deformation parameters are highly correlated. Now, using the same system, I have performed a PCA on this posterior samples. So how that's really done is that I have taken the marginalized Fisher matrix for the same system, and I have diagonalized it using the equation shown here. This directly gives me the errors on the PCA parameters, which is nothing but the square root of the inverse of this diagonal matrix S. Now, if you do the same transformation to the likelihood, it's easy to compute that this PCA parameters are nothing but linear combinations of the original post-Newtonian deformation parameters, which is what is shown here. So this equation also tells that any measurement on the PCA parameter is also a simultaneous measurement on all the PN deformation parameters. So carrying out this transformation on the previous example, the contours are all axis aligned and the constraints are better. So this tells that the correlations between the PCA parameters are lifted, and in turn we have constructed best measured linear combinations of the deformation parameters, which are themselves null variables. So having introduced the method, I have computed the bounds on these parameters as a function of total mass, and I've used the IMR phenom D model, which is in spiral mergering down, which has only quadrupolar contribution and axis aligned spins. There are a few points to look at here. The first is, of course, that the leading two PCA parameters are very well measured, and they're denoted by the black and red lines. It's as good as of the order of 10⁵ for the leading one and 10⁻⁴ for the red one. And another feature which is very clearly evident is that there is a clear hierarchy in the number of PCA parameters you can measure as you increase the mass of your system. It's really the lower mass in spiral dominated systems with which we can do this test best. And if you also keep in mind the accuracies, the errors on these parameters, the best events really are the ones around 10⁶. This hierarchy can also be understood in terms of the information that each of the PCA parameters carry. For example, and this information it can be associated with the corresponding eigenvalues of these PCA parameters. And if you plot them, it shows the similar hierarchy. It just tells that the information carried by the higher order PCA parameters are lesser and lesser as you go to higher masses. Yeah, and another feature is the structure. There are some features. There are some structures in the leading to PCA parameters, whereas the sub-leading one seem rather simple, and this can be understood once we look into the composition of these linear combinations, which is what is shown here. So let's first focus on the left-hand side plot, which is the leading PCA parameter, and the linear combination goes as U1 naught delta phi naught plus U1 2 delta phi 2 and so on. So this magnitudes of this U matrix, the magnitudes of the elements of this U matrix actually tell how sensitive is this PCA parameter to the original post-Newtonian deformation parameters. And that is exactly what I have plotted here. And the main take-home message from here is that the leading PCA parameter is mainly dominated by the first three post-Newtonian deformation parameters, denoted by this black, red and blue lines. The same applies to the second leading one as well, which is shown on the right. However, there is one interesting feature here is that as you increase the mass, the cyan line, which is 2.5 PN log, it pops its head out from the crowd. And and apart from this, the large number of undulations and in these weights are due to a complex interplay of the change in SNR, the change in number of cycles, the changing correlations between these different PN deformation parameters as you sweep through the frequency band. For example, these dips here are nothing but the weights going towards the negative side because of complex change in the correlations. So now let's look at the higher PCA, higher order PCA parameters, which are the subleading ones. So on the left hand side, we have the third dominant PCA parameter, and here the most striking feature is that the cyan line has really come out compared to the previous one here. This only gets more prominent as you go to the fourth PCA parameter, where the 2.5 PN log term dominates. And of course, there's again increased contribution from the 3 PN log and so on. So this only tells that as you are able to measure more of the higher order PCA parameters, you're able to probe the higher order PN, higher order PN coefficients better, and also with good accuracy because of Lisa's good sensitivity.
You have about 2 minutes left, Sayantani.
Sure, I'm actually done. So let me just conclude. So let me just conclude. So I have shown that with Lisa, you can measure up to 5 of the new PCA parameters, and these are nothing but the best measured linear combinations of the PN deformation parameters, and they help us to test the entire PN structure of the of the gravitational wave phase evolution. The most dominant one can be constrained with a 1 sigma error of the order of 10 raised to minus 5, while the second one of the order of 10 raised to minus 3. And the third important point is that this PC assisted test of GR reduces a large amount of computational cost, because this is really one multi-parameter run, and the rest of the transformation is really post processing. There are a few things that I plan to do and is underway. One is analysis with higher modes waveform, because this plots show really more structures as you change the iota and eta. And this is really helpful in getting a sense of where, if we detect, suppose, a deviation in GR, deviation from GR with the help of one of these parameters, it gives you a sense of where is it coming from. So I also plan to do some MCMC runs with non-GR injections to see how well are these parameters able to capture those non-GR injections. So yeah, that's all I have to say. I can take any questions. Thank you.
Thank you very much. That's very interesting. So are there any questions? Or maybe I can ask one to begin with. So would you mind going back? I think it was 2 slides. It's the one where you were showing well, actually, any of these would do, the composition slides. Yeah, thank you. So I was thinking about PCA often being used as a data compression algorithm. So the relevant use there is to consider the different principal components and how much of the total variation in the data the first few principal components describe. So I guess that's kind of related to these plots, but not quite the same thing. So could you comment on that? Like how much of the total variation is described by the first few principal components?
Yes, actually, that is more evident actually from this plot. So this truncations that you see is nothing but what you said. The truncation is happening due to because we're choosing to drop the higher order PC parameters as they carry very less information, even less than. I mean, for example, for a system of 10 raised to 7, the first 2 PCA parameters capture more than 99.9% information. So the rest of, which is what makes the higher order PCA parameters not measurable, and we drop them. What I'm showing is really the composition of this PCA parameter, which is made up of all the 8 deformation parameters. original ones. But yeah, as you said, this part is really the data reduction in the dimensions that's happening.
Okay, and as you explained, that's a function of the total redshifted mass, as described in that plot. Yeah, thank you.
Yeah.
Are there any other questions? Quentin?
Yes, maybe one. I'm not sure I understood. Hi, thank you for this talk. I was wondering, so you are sampling for the PCA parameters, and you've shown as well that, of course, this PCA transformation depends on the parameters themselves. So how do you handle that, right? How do you sample for the PCA parameters, knowing that you have a parameter-dependent transformation? I think I didn't get that.
Yeah, so here we are actually not sampling over the PCA parameters. This is the sampling is done on the original post-Newtonian deformation parameters, which is basically this. Now we really take this, you can really take the Fisher or the covariance matrix of this and do the decomposition on that.
Got
And
it.
that,
Okay.
yeah, and that gives you.
Okay, thank you. Yeah, I understand. Thank you.
Thanks, Quentin. So any final questions? Well, we are a few minutes behind schedule, so let us maybe stop there. But let's thank Sayantani again for a very nice talk. And we will resume at 21:20 CEST, so that's in 15 minutes. We have only 2 talks after the break, so let's take our full 15 minutes of the break. So we'll see you again in 15 minutes. And if I could invite Elie and Stefan just to stay on for a few moments, and we will just give you a chance if you want to check your slides, so that we're all set for the second part. So bye to everyone else. We'll see you after coffee. Okay, Elie, would you like to go first just to share screen to check that we can see your slides and all is well?
Yeah, okay, thank you. I'll try. So this is this one. Can you see it?
Yeah, just fine.
Okay, perfect.
I expected it wouldn't be a problem, but it's just always good to.
I'll just try to put the camera at the same time. Wait, so.
Yeah.
And then we should be good.
I'll just remove the spotlight from me, which.
It's my.
And we can see your camera as well. Perfect.
Okay, cool. Thanks.
Okay, everything is good. Thank you. And Stefan, if you wouldn't mind just doing the same for a moment so that we know everything is good for after the coffee.
Yes. I cannot share yet.
Oh, sorry, Elie, you need to stop. Maybe I can do that actually. Yeah, perfect. Okay, I've stopped Elie sharing, so now it's all yours. Yeah, that's all good. And then
does it look good? It doesn't look good on me though.
Well, you need to just put it into presenter mode. If you can check, you can do that.
I did that, so. And now it goes.
Now it goes. Now it goes just fine.
Try again. Yeah, here we go. Lovely.
Okay, great, excellent. So we'll see you after the break, and look forward to your talk.
Yeah, thank you. How's the audio? Is it good?
Yeah, the audio was fine, and for Elie as well, it was fine. Thank you.
Perfect.
Welcome back, everyone. I hope you had time for some refreshment. And we've got 2 talks in the final part of our session. So it's a pleasure to firstly welcome our first speaker, which is Elie Leroy. So Elie, if you want to share screen. So Elie Leroy is from CEA Saclay and is going to talk to us today about learning-based models for gravitational wave analysis.
Okay, so thank you for this introduction. So I'm Elie Leroy, representing learning-based model for gravitational wave analysis. It's the preliminary works done in my first year of PhD at CEA Saclay with Jérôme Bobin and Hervé Moutard. And so I'm not on the right. Okay. So I'll be presenting. So I may skip over the context of LISA because I guess most people at this attending this talk know much more about LISA than I do. But I'll just go fast on it, and I'll focus more on the problem formulation of unmixing signals in the context of so LISA data and gravitational wave analysis for LISA, and the solution proposed, which is which uses a method called the interpolatory autoencoder, which is a learning-based method that can be used to reduce the dimensionality of some problems, and I'll show how. And the results it gives in data extraction and detection criterion. And so then I'll conclude and present some perspective on my work and on my current and future work. So gravitational wave detection, as I said, I'm not going much about it, but so data is going to be complex with very high dimension signals, and so it will be useful to have some way of reducing the dimension. So the sources, there are multiples. In my work, I've been focusing on massive black hole binaries to actually complement a work done previously by Elie, which was a previous PhD student who defended earlier this month, who worked on galactic binaries. It's also interesting to know that there are other sources, and for instance, for extreme mass ratio in spirals, we don't have yet some very efficient generative model, which can also give weight to methods that don't use a parametric model to be used. And so also, as Tyson presented yesterday in his talk, one of the interesting parts of massive black hole binaries and galactic binaries is that they are highly uncorrelated, since massive black hole binaries exist, are mostly stand out in time domain or time frequency domain, and the galactic binaries stand out in Fourier domain. So this is the Sangria data challenge that Stas presented earlier in his own talk. So basically, there are the chirps and there are the horizontal galactic binaries with the instrumental noise behind. So it's the same plot with only different colors. But it illustrates how unmixing can be a complicated problems in the context of LISA. So unmixing problems relies on finding some uncorrelated representation for every signal. So for every signal. So basically, you want to have something that can make the MCMC stand out, the MBHB stand out from the galactic binary, from the GBs, and the other way around. So in the state of the art, most methods rely on, well, currently most methods are parametric methods, which use Monte Carlo Markov chains, which provides the advantages of being physically relevant, giving the actual physical parameter of the system, and also enabling the exploration of the parameter space, and providing the some uncertainty quantification by giving boundaries and some insight on how the error propagated in the results provided. But they have a major drawback in that they are very costly, since they rely on multiple calls to the generative models, and so generative functions that can have a high computational cost. And especially for, so for instance, the possible tens of thousands, the hundreds of thousands of parameters that will need to be evaluated, since one massive black hole binary is, is described by 16 parameters, and one galactic binary is described by 8. So another way, which was presented by Sayantani before, is so our non-parametric method. So for instance, the principal component analysis or wavelet transform decompositions, which are actually ways to have a lower dimensional representation of the signal. So they are fast and they don't rely on generative model. Well, they are fast because they don't rely on generative models. But one of the limits of those methods is that they are linear with respect to the input signal. So they can't have the flexibility that will have nonlinear methods. And so that's where our approach inserts itself in this context. Our goal is to learn low dimension nonlinear representations of the signals to have actually to have the advantage of the non-parametric methods, but going one step further by having something that can be better at actually extracting the signal, and that sticks closer to the signal than taking a linear model. So low dimension representations, so as I said, are well adapted for so high dimension problems. Well, which is the case for ELISA, because one signal is tens of thousands. Well, one signal can have a high dimension, which are described by few parameters. So 16 and 8 is pretty low compared to the number of observations for each system. And so actually it's a way that it's a useful tool to tackle multiple problems, because once you have a good representation of the system you want to model, you can use this representation to do multiple work. So for instance, detection, extraction. So for unmixing, it's also important to have a way to have different different representation for each system. So previous work was done on galactic binaries, as I said. So here there's the article, one of the articles she published that can be found here. And so our objective now in my PhD is to moving on to MBHBs. So the method that I used was based on autoencoders. So this is a quick overview of what an autoencoder is, but don't worry if you don't know about it, because I'll go further into it for the 3 next slides. But so it's basically a way to use neural networks to reduce the dimension of the data. So my work has been focusing on a method that's called the interpolatory autoencoder. So it relies, as most autoencoder, it relies on dimension reduction using neural networks. And so in this case, it goes from the observation that the data exists on a low dimension manifold, which is immersed in a high dimension direct space. So observation space, basically. It's the number of the direct space is the dimension of the direct space is the number of observation or measurements you did with your instrument. And so each signal can be represented as a point in this on this manifold. So A1, A2, and A3 are called anchor points. They are basically pure signals that, so in this case, pure MBHBs, not contaminated by noises or galactic binaries. They are what we want to have as the output. And the X-in, which will be the input of our autoencoder, is this is a noisy signal, and that's why it doesn't exist on the manifold. It's a bit off from it, and we want actually as a denoising process to put it back on this manifold. And so A1, A2, and A3 are called anchor points, which will be used to have a vision, an estimation of this manifold using some interpolation on them. So from this direct space, there is an operator phi that's which will be a neural network, which goes into a latent space in which the signal is much more ordered than in the direct space. In the direct space, the manifold is complex. In the latent space, we make the hypothesis that it's flat, purely flat. It's an affine plane. And so in this affine plane, we can actually project which we know from the transform of the anchor points. We can project the transform of our input, which was noisy, onto this affine hull from the anchor points. And so this projection can be made orthogonally, which will be the fast interpolation, which is just an orthogonal projection onto this affine space. Or it can be done a bit more smartly by using a barycentric span projection, which will try not to minimize the distance in the latent space, but trying to minimize the distance in the direct space. So after that, there is a decoder part. So phi was the encoder which went into the latent space, and psi is the decoder which goes back into the direct space to give us a signal that we can use And so basically, phi and psi are both learned simultaneously by minimizing the function that's below. So one is so there are two terms in this loss. One is that we want x in the input and the output to be close one to another, because so it's unsupervised learning. We don't need to add labels to our data. We don't need to know what's in our data, but we want actually that after it went all this in all this, it comes back close to what was inside of it. So for the training part, of course, during the training, but we also want that in the latent space, all the training data are close to the manifold generated by the anchor points, because this means that we have something that's actually flat and not just supposed flat without having much to justify it. And so this is the minimization we do to train our neural network. And after it's been trained, we can use it to actually denoise and to represent in a lower dimension the data. So for the implementation, the encoder and the decoder were convolutional neural networks, which gives a bit of a tricky part where we need to introduce lateral connection to actually have the training part. But so there were 5 layers convolutional neural network. So it was not a big, it's not a deep neural network. It's a pretty small one compared to what can be found in the literature and in some huge tech company which have high computation power. And so it's actually, I think it takes a few hours to train. So it was trained on the 1,000 centered massive black hole binaries taken, so 500 points at sampled at 5 seconds. So it was 2,500 seconds around coalescence. And we took 30 randomly selected anchor points in the training data to model the signal, and it was tested on 250 massive black hole binaries with different noise levels. We tried extraction and detection to benchmark our method. So for signal extraction,
you have about 2 minutes left, Elie.
Okay, yeah.
Thank you.
So for extraction, we just it was just taking the output of the neural network, and we see that actually it helps to denoise the signal. So this is the same MBHB for each column, but so for fast interpolation and for barycentric span projection, but also with varying noise levels. And so we see that the higher we go, the best we are, with actually some a plateau which is reached because the lower dimension actually blocks the performance at some high SNR values. And so for the detection, we tried hypothesis technique. We used hypothesis testing. We generated noise only and noise plus signal models. We tried to put it into the IAE, and then we measured. So in this case, the SNR of the output. So the signal to noise ratio of the output of at the end of the IAE. And so by fixing the thresholding, because we knew what for the false positives, because we had some what the output for noise only, which gave us the idea of how noise propagated into our autoencoder. We could fix a false positive rate, and then they say that everything that's below is can be considered as compatible with noise, and everything that's above is not compatible with noise, so should be signals. So this we had some good results on detection. And so to conclude, so this was preliminary results on MBAP analysis for LISA data using a convolutive interpolatory autoencoder. It permitted to have extraction and detection of the signal around coalescence. And so for my ongoing work and perspectives and my current perspectives, so it's I've been working on extraction during in spiral to go further before the coalescence than only 2,500 seconds. So also to have a full unmixing pipeline, we need to combine MBHB representation with galactic binary representation to, for instance, tackle Sangria data and compare with, finish the comparison with PCA and wavelet transform, which are used in other parts, in state of the art. So thanks for your attention, and if you have questions, I'd be happy to answer.
Thank you, Elie. Very nice talk. So already there's a question in the chat. What's the dimension of the latent space? So could you answer that?
Yeah, so the latent space in our work is the same as the direct space. The transform does not reduce the dimension. Phi does not reduce the dimension. It just rearranges it, and then the dimensionality reduction happens when we project onto the affine space generated by the anchor point, which is then of dimension 30 in my work.
Thanks, Elie. Are there other questions? Okay, well, maybe I could ask one. I guess it's a proof of concept study and very nice. And could you say a little bit more about the training set that you use? So the question I have in mind is, do you have any sense of the usefulness of the method for different masses of massive black hole binaries? You know, did you consider a range of masses in the training?
So currently we've been working with masses from, I think it was 10 to the power 5. So chirp masses of between 10 to the power 5 and 10 to the power 7, if I recall correctly. And so actually, yeah, in this work, I've been working with only 2 parameter shifting, chirp masses and mass ratio. Okay. And the mass ratios were between 1 and 10, I think. Yeah, 1 and 10. Okay. And so there's the question is, one of the questions we had was, what would it be interesting to train different models, like to have different auto encoder and decoders for different ranges of chirp masses, because we know that the signals can vary greatly between one and the other. So it's one of the questions we're currently discussing.
Okay, good. Yeah, that was one of the reasons for my question. So I'm glad you're looking at that. John has a question.
Yeah, thanks for the interesting talk. So it's along the same theme. There's been quite a lot of work in the context of ground-based detectors on reduced bases representations of waveform models. And the equivalent here is the dimensionality of your anchor point space, I guess. So how did you choose 30? Or did you try different values and this one was the smallest that worked, or did you just pick 30 and then?
That's a very good question. So actually, the anchor point, we don't yet have a foolproof strategy to choose the anchor points regardless of the problem. So for the galactic binaries, what was done was that they had so they could choose a lot and then reduce by applying, for instance, some sparsity constraints and reduce the number up to a lower number, which was so the best anchor points from the big sample they had at the beginning. In my case, we tried to do that at the beginning, but it was not very useful because we witnessed that not every with one set of anchor points chosen, not every massive black hole binaries was using the same. Well, all the anchor points were actually used. The less you have, the lower the dimension, but also the more you risk the more you will lose information. So maybe to have an idea of the number of anchor points we can go to, it could be interesting to have, for instance, some kind of PCA or some kinds of other mean of knowing what kind of order, what kind of number of anchor points we want to have. But so yeah, there's that, and there's also the possibility to use anchor points which are physically relevant. So for instance, taking some extreme values of the parameter space that we had in the beginning. But yeah.
I see. Is it just a coincidence that it's approximately the square root of the size of your training set?
Yes.
Okay.
Okay.
Thanks.
Right, well, thank you. I think we need to move on, but thanks again for a very nice talk, Elie. Let's thank Elie again. And that brings us next then to our final talk of this session, which is by Stefan Strub. So I'll invite Stefan to share screen and then we'll introduce him properly. Okay, so it's a pleasure to welcome Stefan Strub from ETH Zurich, and he is going to talk to us about accelerating parameter estimation of galactic binaries in the full LISA frequency band using Gaussian process regression.
Hi, everybody. Thank you, Martin, for the nice introduction. Yeah, exactly. I'm talking about accelerating the parameter estimation using Gaussian process regression. And here you see like a neat picture of LISA. So whenever LISA will be in space, we need to have tools on how to analyze the data set. And yeah, we already had a lot of talks by Tyson, Stas, and Michael about what the LDC is and what the galactic binaries are. So yeah, I can skip all this introduction a bit. So this will be how the data set will look like, a snippet of it in the frequency domain. Here we see one of the TDI components and the data in black. And in gray, we have all the injected signals, which are within these frequency band. So here we see all these dots, which are injected, about 20 signals in here. And the goal is like to extract as many data as possible. And how can we do that? We can do that by having like, okay, we have a function with which we can simulate the LISA response. So we can put in a parameter set of 8 parameters for galactic binaries, simulate the signal and compare it to the data D. And the better the match, the better is the value of our log likelihood function. So in the end, we can have an optimization problem where we want to optimize this likelihood function, which then gives us our best match. So one way is to do that by doing it with a best fit. So we're only interested in the best fit of the data. So we can do that with differential evolution. Then we need like around 20,000 function evaluations of the log likelihood functions for that. So it's rather fast, but we do not get an uncertainty estimate. On the other hand, when our goal is to have a Bayesian posterior distribution, we can do that with Markov chain Monte Carlo method, but this is rather slow, where we need like a lot of function evaluations in order to compute that. But on the other hand, we get our uncertainty estimate, which we like. So my goal here is now to convince you that there is a way that we can combine the best of these two worlds, where we take the result of the best fit and use that knowledge about this result to speed up the computation of the posterior distribution. So how can we do that? Here we start with a simple case where we have the data with noise and one injected signal. The injected signal is shown here as a gray line below the blue line. And when we throw the differential evolution algorithm on it, we get this blue line, which is overlapping very well the injected line. So we're happy about that. And this MLE, the maximum likelihood estimate, looks in the parameter space like this as a green dot. So this is now shown in the sky location only, but it actually is in 8 dimensions. And now we want to go from this dot here to our posterior distribution on the right, because that gives us our uncertainty. So we can do that by reducing the parameter space around the MLE, because we know like we're actually only interested in this reduced parameter space. By taking the inverse of the Fisher information matrix, we get an estimate of our uncertainty distribution. And when we take for example, the 3 sigma boundary around this MLE, we can say like, okay, we're quite confident that our posterior will lie within this region only. As we can see here, these 2 red boxes. And then what we can do then is to just sample 1,000,000 times within this box with Metropolis Hastings algorithm. And what we get is this posterior distribution. But this takes a long time. It's like takes hours, and it's long. So we can speed up that process by using Gaussian process regression, with which we model the log likelihood function in this reduced parameter space. So we have like around 1,000 or 2,000 training samples within this 8-dimensional reduced parameter space, train our model, and then we can evaluate that log likelihood function quickly from our model. And that then gives us our posterior distribution with millions of samples within minutes. So that's very nice and very much of a speed up. So again, as we see, like we have a single signal, we get a best fit. From the best fit, we get a posterior distribution, all nice and neat and fast. But maybe you're not convinced yet. Maybe you say like, this is only a single signal. What about overlapping signals? Here we go. This is now 2 signals. The first signal, as just shown before, the blue one is still here. And now we added a second one. So what happens when we throw the differential evolution algorithm on it? We still found the blue one, but it's a bit different. It's like there's a bias induced from this secondary signal. And then as the red line, we have the residual, where we say like, okay, we subtract the blue signal, which we found from our data. And if we looked at, okay, it doesn't look like it's on noise level. It's like still there's something in it. So it's like, okay, let's run it again. Let's throw the differential evolution algorithm on it again and see what happens. See here, we find this orange one. So, okay, how does that look like? Let's subtract both of them from the original data and see what happens. We see like, okay, this red one still like, there's still a bump in it. It doesn't look neat. And also the blue one doesn't match well. So the bias is there. So what can we do? We can do a global optimization with these 2 signals here as an initial guess, because the thought is that like, okay, these 2 initial guesses are actually quite close to the global mode of like these 2 signals together. And we can do that, and we see now, oh, hooray, the blue one and the orange signal, they're actually matching quite well, and our residual is actually at noise level. So we are very happy about that. And does this also like get rid of the bias for the posterior distribution? Now shown here is the posterior distribution. The blue one is the same one as shown before, and the red one is now the posterior distribution of the first signal, still the blue one, but initially the data contained both of these signals. And then when we subtract the orange one from our global fit, we see like, okay, that our posterior distribution has the bias quite remarkably removed, especially in the sky location and frequency derivative, not as much in the amplitude and inclination, but they're still like good overlapping. So we're happy about that. So this is an example of two signals, and they were like quite in the middle of the window we set, but what is like the whole LDC, like the LDC14 with like 20 million signals in it. Okay, let's look at a section of that where we say like, okay, we have 4 of these windows split by these red lines. So like we have this first window would look data all the way to this neighboring middle line. So it would receive data all to there, but it would only accept signals which are within this blue region. And the same goes for this one. So let's call these blue ones odd windows, and these neighboring in between the odd, these are the even windows and these are the odd windows, right? So let's throw our algorithm onto the even windows and see what happens. Okay, we see we have a green result, blue, and the orange one from the first one, but only the blue one is within the shaded region. And on this side, we have the red, brown, and the purple one. And then we also have this gray one, which is coming from the signal all the way to the right, from the window all the way to the right, which is actually not plotted. But we see like, okay, we're not interested because these are plotting the same signal twice, but it doesn't matter for us because we're neglecting that. We're throwing it away. We're only interested in this red one and the blue one. So what we can do is we subtract these two signals and we get the residual shown in CN, and then we can throw that again into the odd windows one and repeat it. So now we get all these signals. We only have, we only have this one orange signal, which is outside of the windows. All the other ones we accept. And now let's repeat it again with the original data. And now we see, okay, let's do the evens again, where we subtracted the odd signals we found in the odd windows. And let's see again what happens. Okay, we get this orange, blue, the green, and the red. So we're happy. We can combine all these together, and this is what we get. We find all these signals, even like in this like huge overlap, we get a lot of signals out of them. And in total, we find 14 out of 20 of these signals. So yeah, this is all about the method. But now let's talk about like the performance. Let's talk about numbers. We like numbers. So if we do that for the whole Radler data set 1.4, then there are like 26 million signals in there. They're like a lot. So we restrict ourselves to 0.3 millihertz up to the Nyquist frequency. 0.3 because here is like even the instrument noise is like higher than most of these signals. Like there's not much use of going lower than that. And in this region, we have 6.8 million signals, which are quite a lot. And we're not expecting to get all of these since like most of them have like a super low SNR. So let's say like we are only looking at the ones which have an SNR above 10. So they're like about 18,000. So like that sounds realistic. So let's look what the pipeline throws out, and we find almost 19,000. So a bit more even than we expected, which is quite nice. And let's see now how well do they match? Like does like these signals which we found, does it have a companion of the injected signals? And we can check this companion with the correlation function down here. If we say like the correlation is above 0.5, we accept it as a match. It has a companion which was injected. And we see that we have 16,000 of these got matched, shown in green. And we have 2,000 of these, which are ambiguous. They don't really have a companion. They're not matched. And in the end, we get a match rate of 88%. So 88% of all the found signals are matched. And here now in red, I'm showing you the injected signals which do not have a match. And now this plot is interesting because we can see like, oh, okay, all these loud signals, we can match them well. Down here, no chance. And here in blue, we have a confusion cloud where like a lot of signals are overlapping. So like most of our like ambiguous signals are over here. Then here we also have a region where we have these two highest frequency ones did not get a match. Why is that so? There's actually, the reason is for that we plot it, when we plot it, in black the data, and in gray we have all the injected signals in there, like given from the parameters from the LDC, from the data challenge. We see that it actually does not match the data. So we do actually expect that the signals we're finding, which are trying to match the data, are not matching these parameters of the injected signal. And this as well for the second highest frequency. So we are actually not concerned about these. We're actually happy that these two did not match.
You have about 2 minutes left, Stefan.
Yeah, thank you. So now let's talk quickly about computational time. So yeah, there was a question before from Jean-Baptiste, and I have some answers, like how long it took for me. So the even one where we restricted the first one up to 3 signals, it took 1,500 CPU hours, the odd ones 3,000, and the even ones 2,400. And in total, we get about 7,000 CPU hours. And the good thing is now that we can actually parallelize this whole thing. So this is all like these have not neighbors like which are connected. So if we have a CPU, like if we have 3,485 CPU kernels, we can run this all in parallel, and then we would get computational times of about 27 minutes. So in total, all that together, we have 2 hours, and we get this signal, like all these found sources, which is quite nice. And then we can also do that for half a year of data. Just now it was always with 2 years worth of data. Now you can see if we switch forth and back, the cloud actually is moving down when we're going to half a year. So the SNR is getting lower. So we're actually expecting to find less signals now, 6,400. And we got about 8,000, and we have quite a good match rate of 91%. So this is quite nice. And to conclude is that, yeah, we have, I hope I convinced you that there is a way where we can have a Bayesian parameter estimation as soon as which is fast, as soon as we have like all the signals in there which are loud. If we match them quite well with the best fit, we can subtract them, and just with the remaining one, we can quickly get our Bayesian parameter estimation within minutes. And we can also all like parallelize that. We have a robust pipeline to extract the galactic binaries, where we find a lot of signals within the 2 years worth of data. We have low computational costs. Also the low latency, because we can parallelize it. So the full galaxy we have within 2 hours. And it can also be time evolving, or like it is actually in time evolving, where we say like the previous searches, signals, we can use them as initial guess for a later stage. And that further speeds it up. And yeah, I'm happy to take questions.
Thank you, Stefan. That was very nice. So as Stefan says, are there any questions? Looks like we have a hand up, and that is from Jesus. So over to you.
Hi, Stefan. Very, very nice. Oh, sorry. Hi, can you hear me now?
Yeah.
Yeah. Very, very nice talk. I'm working on Gaussian process regression applied to Bayesian estimation in a different field, not in gravitational waves. And I was wondering, so for us, getting a Gaussian process to actually converge and reproduce the distribution that we are looking for is not trivial, and definitely not trivial for. Do you have like 6, 7 dimensions?
8.
8 dimensions. So, do you find any problems there, or with your 1 or 2,000 samples always converge precisely?
So what I'm doing is I start with 1,000 samples, and if I don't, I have like 5,000 which I test my model with, and if I don't have a good RMSE, then I get like if I have a high error, then I repeat it again with 2,000 more, and repeat it again up until 4,000, and usually within 4,000 I have good accuracy.
And I reckon you're using something basic like a scale, basic, not in the bad sense, but I mean not using CPU, for example, like a scalearn or GPy.
No, it's all on CPU, actually.
It's on CPU. So it's a Gaussian process with 1,000 samples is not very fast to evaluate, even to evaluate, right?
It was okay. I did it with scikit-learn.
Yeah, I also use it.
There's like 1 microsecond or so for if I have 1,000 training samples.
Okay. Well,
yeah.
Okay.
So just one suggestion, like I think it's important. You have if you're using Gaussian processes, then you can get the derivatives for free. So maybe you want to swap your MCMC on the Gaussian process by, for example, Hamiltonian Monte Carlo, and you can actually converge with many fewer evaluations. Just one piece of advice.
Thank you.
Okay.
Thank you. Thanks. Interesting. So let's go to John now.
Hi, Stefan. Thanks for the nice presentation. I noticed that you had a number of sources that were found but not matched that had quite high SNR.
Yes.
Do you understand what they might be? I mean, it looks in this figure, for example, that those 2 injected not matched sources at high frequency might have just been split up into a bunch of lower SNR sources. Does that explain some of the others as well?
Yes. So, for example, where you have like, it's not always perfect. So like, for example, rather these ones which have a pair with an injected, which is not matched, there you can say like, actually the differential evolution algorithm is not perfect, right? It's like, it has like a match, a success rate of like 90%, let's say. So I'm actually repeating it 3 times for each signal. So there, with that, I get a like success rate of 99.9%. So out of still like 18,000 signals, I still expect that I get 18 signals which are not perfectly like finding the best fit. So this is it for these pairs. For these, yeah, it's like a bit like you said, that there is getting something is matched. Like there's also like with noise, there's something like it can build up. Actually the match is way higher. So the match gets a way better SNR than the actual pair it would get. So also just the amount of signals can by coincidence build up a signal which is not there.
And is there any way to diagnose that that's happening, or is it just something we have to live with?
I don't know yet. Well, okay. It's definitely, you can say like, okay, in this like low SNR region with at this frequency where you have this confusion cloud, you have a higher chance of being ambiguous. So there you can even say like, okay, like this is like the ratio of being ambiguous, because yeah, we don't know it with the real data. But up here, you could be saying like, okay, I'm quite confident because like 99 out of 100 signals are good. So with this simulation, at least.
Okay, thanks.
Yeah, welcome.
Okay, thanks, Stefan. So we're a little behind schedule, but it was an interesting discussion. Seemed a pity to cut it off there. Let me just check. Are there any final questions? Time for maybe one more. Well, let me just ask one, which I'm curious about. So your matching criterion is a correlation coefficient of greater than 0.5. So how does your matching rate depend on that choice? If it was, for example, 0.6 or 0.7, how would that change the matching rate?
Yeah, if it would be higher, the matching rate is better. It's higher, but I would, yeah, definitely also get more rid of these like 16,000. It would go lower.
Yeah,
I actually have a histogram plot right here ready. So here you see the histogram of the correlation. So you see like most of the signals live up here. So if I say I would cut it off at 0.7, for example, I would get rid of like 1,000 signals which are living down here, but I get a better match rate.
Yeah, I was wondering, as John asked his question, whether the variation with the correlation coefficient might be some kind of diagnostic tool for misclassifying. I don't know, but it would be an interesting thing to discuss more. Anyway, let's thank Stefan again, first of all, for a very interesting talk. And let's thank all of our speakers and indeed all of our audience for sticking with us. I think there's a final talk just going on in some of the other sessions. You're welcome to join that if you have time. And of course, don't forget to join us again at 11 o'clock Central European time tomorrow morning for our next plenary session. So with that, I will sign off and thank everyone again.
Thank you.
Bye-bye.
Thanks, Martin.
Yeah, thanks, Mike. Yeah, thanks for all your help. I think that went fine. Were there any YouTube questions? I assume, you would have popped them in